Good morning, good evening, and good night, or good afternoon, whatever you might be. This is the notes for chapter 19, which is all about pressure, and especially liquid pressure. And we're going to start off with just the formula for pressure. It's going to be force divided by area, or you can simply take P for pressure. It's not power anymore, so be careful that you don't get those confused. Equals F divided by A. I don't know why my writing is so squiggly here today. So it says, what is the pressure? So I'm looking for P on a 2 square meter desk. So the area is going to be 2 square meters. It's going to be my A. If I am sitting on it with 1,000 newtons of force, that sounds like a lot, but you know, I got pure muscular mass. So this is going to be my F right here. So I'm simply going to put in those numbers of 1,000 newtons divided by an area of 2 square meters. And you're going to get 500 newtons per square meter. Now, a guy by the name of Pascal came along and said, I want it to have a unit, so therefore they named the unit after him, and so we measure pressure in pascals. And we get into liquid pressure. Actually, before we do that, one of the things I'm going to have you do in class is sit on a nice little bed of nails, and you wouldn't dare sit on one nail because the area is so little. So the littler this is, the more force goes up because you have more pressure on that particular nail. But you would sit on 400 nails on the bed of nails that I gave you, because the area goes up as this A right here increases, then pressure goes down. So once again, if area increases, so if you have more nails, pressure on each nail is going to go down. So it won't go up, the nails won't go up into your derriere. All right, in the next one here. We now get into something. I don't see a thing on here. Hold on, let me pause and see what's going on. Now with liquid pressure, it's a little bit different. The formula is going to be pressure equals weight density. And I don't know why, but some books use that rho again. So it's not going to stand for momentum. It's going to stand for weight density now, times the depth of the water. So, or the depth of the liquid. So it says you're 5 meters underwater. So this is going to be my D right here. Sometimes they use H for height too. What is the pressure on your body? Well, you got to know the weight density of water. Well, you got to remember the density of water is 1 gram. Remember for water, density was 1 gram per milliliter. Well, that means it's 1,000 kilograms per cubic meter. And so with pressure, you got to put in kilograms and cubic meters. That rho is now going to be 1,000 instead of 1. So be careful that you don't get that confused. Per cubic meter. Multiply that by your distance underwater of 5 meters. And so you end up getting a weight density, oh, I'm sorry, times gravity. We forgot to, since weight density, that's the density of water is this rho here. The weight density is going to be times gravity. So you got to multiply this by 9.8. When you put all that together, your new weight density is going to be this 49,000 pascals, which would write that in here, 49,000 pascals. Now, a lot of times we put it in kilopascals because pressure is so many pascals. And so put it in kilopascals, you're going to divide this by 1,000. So there are 1,000 pascals in 1 kilopascal. You put that in black so you can see a little bit better. I don't know if that's helping or not. So this is 1 kilopascal. And so that ends up being 49 kilopascals. Now, the one thing I want you to know is that the amount of liquid around you does not determine the pressure. So if you look right up here in this picture you see of the lakes, you have a very, very deep lake and you have a shallow lake. Well, even though the shallow lake here has a lot more water around it, okay, that one has a lot more water, this one has more pressure because it's deeper. So it's how deep you are that determines the pressure and its density, not how much water is around you. So even if you look at these fishes down here, okay, let's look down here. You've got the little dory down here in the lower left-hand corner. She's much deeper than, was it marlin or, I think it's marlin right here. he's a lot shallower. So even though he has more water around him, that's not what determines the pressure. She's actually got more pressure because she's deeper. So when you build a dam, I'm looking at this one right here, a dam must withstand the depth of the water behind it, and not which one has the most water behind it. So a lot of times what they'll do when they build dams, they'll make them curved, not only, so if this is your dam right here, the bottom of the dam, let me draw this in a different color. So the bottom of the dam will go down like this, because water always pushes at a right angle to the surface. So when you have the water coming here, you know, the water would push like this and push like this. Well, as the dam curves down, it's going to start actually pushing the dam down into the ground. And so that way it you know, doesn't want to just keep pushing the dam backwards. It actually pushes it down, which gives the dam more strength. And so you know, as the fish come along here and they run into the dam and they say, "Damn!" That's because they ran into a dam. Then once again, all the pressure is pushing at right angles to that. So at any point, the forces that produce pressure are always exerted in all directions, and they're going to be done at right angles to a surface. Okay. Now, what we're going to be doing a lab on today is buoyancy. And if you notice, when you jump in the water, sometimes you feel like you weigh a lot less. If you go into aqua therapy or doing any type of therapy, they often tell you to work out in a pool. It provides a lot of resistance, but at the same time, it's a lot easier on your joints because they don't have to lift as much weight. So buoyancy is this apparent loss of weight whenever you due to a buoyant force whenever you're in a fluid. So I want you to look at these objects that they're putting here. And I got a rock, or it looks like a potato that's getting ready to go in a beaker of water. And when they drop it in the beaker of water here, if you notice, the water comes out. Well, the volume that is displaced is equal to the volume of the object that's in the water that sinks. Okay? Well, the other thing that's interesting, this is what Archimedes' principle states, and that's what you're going to learn today in lab, is that the weight of the water displaced, I'm going to say fluid instead of water, so the weight of the fluid displaced. So if I were to weigh that water that came out of that beaker and is in the scale, that's going to be equal to the buoyant force, or how much force pushes up. So let me give you a great example. Let's say this rock weighs, I don't know, 10 pounds. Well, let's say 10 newtons since keep it metric. Okay? But you had 2 newtons of water that came out into this little jar over here. Well, that 2 newtons that is displaced is now also equal to the buoyant force that pushes up. Well, that means if you have 10 newtons pushing down, and you subtract the 2 newtons that pushes up, okay, that means in water, that rock is only going to weigh 8 newtons. Okay, so the rock's going to weigh a lot less. Well, let's say that you displaced the same amount of water that, or you had a buoyant force that was equal to your weight, for instance, like a boat. Well, if you displaced 10 newtons and your boat only weighs 10 newtons, that means your boat's going to float. So all floating objects, that's what's written down here in red, all floating objects displace a weight of water that's equal to their own weight. Now that's why an aircraft carrier that's made out of concrete and steel can actually float, because a lot of that boat's underwater and it's pushing away more water than it weighs. So its buoyant force is more than it weighs. But if you get a hole in the boat and it can't displace the water because the water starts filling the boat up, then you'll start weighing more than the water you displace and you sink. And so that's Archimedes' principle of flotation and Archimedes' principle. Right? And the last little thing we're going to talk about today is Pascal's principle. And you'll see that I have this 2-liter bottle that has a little Cartesian diver in it. We'll show you that in class. But what it explains is that any change in pressure in an enclosed fluid, so I'm going to close up a 2-liter bottle, and when you squeeze on it, all the pressure increases all over the whole bottle. So if you had a 2-liter bottle here, let's draw a pathetic bottle. So here's a 2-liter bottle. Okay. Let's just say I squeezed the bottle and the pressure went up by 10 newtons per square meter down here. That means it's also going to go up 10 newtons down here. And it'll be 2 newtons over here, and 10 newtons right here, And so all over the whole bottle, the pressure is increased. This is called Pascal's principle. We're going to use this to build a hovercraft because we can lift large amounts of things with small pressures if we spread them out over large areas. So let's look at this picture you got here. On the right-hand side, I have a pressure that has a small force of 1, so my force equals 1 here. But my area also equals 1 over here. Well, if you remember, Pascal's principle says that the pressure is transmitted undiminished to all points of the fluid. So if I have a really large weight over here of 50, if I spread that 50 newtons over a really large area like my hovercraft of 50, you see how the pressure is the same? 50 divided by 50 is 1. 1 divided by 1 is 1. And therefore, I can lift really large things. Well, let's look at this formula over here that you see that the pressure out equals the pressure in, or the F over area, force out over area out. So we're going to take that the pressure is always got to be the same for Pascal's principle. So I'm going to say the force number 1 and the area number 1 has to equal the force number 2 and the area number 2. It says the force is multiplied over the area using pressure, therefore placing 10 pounds on 1 square inch. So I got 10 pounds on 1 square inch. That's an N. Means I could lift 100 pounds on 10 square inches. So once again, the more I make this piston, the bigger I make the piston, the area over here, the more weight I can lift. So when you go into a automobile mechanic and they lift your car up on that great big lift, this is what it looks like under the ground. It's this huge area of a piston that goes up in the air. They're spreading that force over a really large area so they can simply lift your car with a little air compressor. Okay? We'll show you some videos of cars that use hydraulics and jump up and down, things like that. Hope this helps. Have a great day. Bye.